What is the stress and strain relationship in structural analysis? Imagine a structure like a bridge or a building component being subjected to various forces during its lifespan. These forces cause internal responses within the material, which are crucial to understanding how the structure will perform under different conditions. To analyze these responses, engineers examine two fundamental concepts: stress and strain. Stress refers to the internal force per unit area within a material that develops in response to external loads. It is measured in units of force divided by area, such as pounds per square inch or pascals. When a load is applied to a structure, the material experiences internal forces that resist deformation. These internal forces are distributed throughout the material, and their magnitude depends on the type and magnitude of the external load. For example, tension causes the material to stretch, compression causes it to shorten, and shear results in sliding layers within the material. Strain, on the other hand, describes the deformation or displacement experienced by the material relative to its original shape or size. It is a dimensionless quantity, often expressed as a ratio or a percentage. For instance, if a steel rod is stretched by a certain amount, the strain is the ratio of the change in length to the original length. Strain provides insight into how much a material deforms under stress, which is essential for assessing whether the material remains within its elastic limit or undergoes permanent deformation. The relationship between stress and strain is primarily characterized by the material's elastic properties, which are described by the elastic modulus, also known as Young's modulus. This modulus defines the proportionality between stress and strain within the elastic limit of the material. When a material is loaded within this limit, the stress and strain are directly proportional, following Hooke's law. This means that doubling the applied stress results in doubling the strain, and the material will return to its original shape once the load is removed. However, if the applied stress exceeds the elastic limit, the material enters a plastic deformation phase where the relationship becomes nonlinear. In this phase, additional stress results in permanent deformation, and the material no longer follows the simple proportional relationship. Different materials have different elastic moduli and yield points, which influence how they respond to applied forces. Understanding the stress and strain relationship is vital for predicting how structures will behave under various loading conditions. It helps engineers determine the maximum load a component can sustain without permanent damage and guides the selection of appropriate materials for specific applications. By analyzing the stress-strain curve, engineers can also identify the elastic limit, yield strength, ultimate strength, and fracture point of materials, ensuring safety and durability in structural design.